Okay, so I'm just going to go backtrack a little bit. So we're talking about the rectangular coordinate system. It is the right-hand coordinate system. I'm going to stop the video just for a second so that you can see what I'm talking about. Okay, so it looks like this. So for you, it's a little bit backwards, but this is the x-axis, here is the y-axis, and this is the z-axis. So the pointer finger, the y goes kind of into the wall, and the z goes up, okay? All right, so that's the axis. Okay, so we can talk about a couple of different things. So let's talk about a few regions, some general regions. So if I say z is greater than or equal to 0, that means I'm looking at everything that is above the XY plane. Okay, so this is the XY plane and above. Or the upper half space. Okay, if I have x is equal to 3, so this is a plane that's parallel to the YZ plane, and it's 3 units away from the YZ plane. Okay, if I talk about -1 less than y less than 1, so this is the region of space between and not including the planes y equals -1 and y equals 1. So this one actually kind of looks like down here where y is equal to -1, I might have a plane. And this plane goes on forever. So it's actually parallel to this plane. Uh-oh, that's square. So here's another plane, but this one cuts through at y equal to, instead of y, this one cuts through at y equals 1, this one cuts through at y equals -1. And so these are parallel planes. Okay. All right. So let's say, how about this region? X squared plus y squared is equal to 1. Now, let's think about this for a moment. So on the XY axis, where z is equal to 0, This is a circle of radius 1. So down here, I have a circle of radius r equals 1. But I have that same circle at the height z is equal to 2. So notice this is the center. Stop it. This is the center of this circle at z equals 1. Z equals 0. This is the center of the circle at z equals 1. I would also have the same circle at z equals 2. I would also have the same circle down here at z equals -2. So to be honest, I actually have the same circle for all z. So therefore, if you really, what we really have is we actually really have a cylinder. So I actually have a cylinder. Okay, so I actually end up with a cylinder. So this is a cylinder. Of radius equal to 1. So no mention of z in the three dimensions means it happens for every z. Okay, so let's look at vectors in space. I'm going to go back and grab this picture. Okay, uh-oh. How did it didn't grab the whole thing? Well, that's bizarre. Ugh. Still ain't right, but Okay. All right, so how do you find a vector in space? Well, this vector, if I go down here to X, and then I go over here to Y, and then I go up here to some value of Z, and I get this point P being X, Y, Z. I can then talk about the vector that goes from the origin to that point. So the vector, so 0p, so R equals 0p is the vector that starts at the origin and ends at the point P. And it says go over X, go over Xi plus Yj and then Zk. Okay, so go over X and then Y and then Z. So that's how I get to that vector. Okay, and just like before, so for any vector, so this is called R3. Okay, so any vector A1, which looks like, for any vector A, that looks like A1, A2, A3, and any vector B that looks like B1, B2, and B3, and these are both in R3, then I can take the vector A plus B is to take vector A and add it to vector B and get A1 plus B1. That's the I component. A2 plus B2. That's the the J component, and then A3 plus B3 is the K component. All right, so I can write this as A being A1I plus A2J plus A3K.
Samuel Crumpler.
B being A1 B1I plus B2J plus B3K. Then I can get A plus B is A1 plus A2I. A1 plus B1. A2 plus B2J. And then A3 plus B3K. So I can write it in either form. So I can have it in this form, or I can have it in this form. But they're both the same. Okay. So the vector between 2 points. So let's look at the vector between 2 points. want to go back and call that vectors in space. Okay, so now let's look at the vectors between 2 points. So we want to go back to our original okay. So I'm going to choose a point and I'm going to draw the vector to that point. And this is going to be P2. And it's going to be X2, Y2, Z2. That's the point. And then I will choose another vector. I'm going to call this one P1, X1, Y1. Okay, and so those 2 points. So what's the vector between them? Okay, well, the vector between them, say we want to start at P1 and go to P2. So I'm going to start at P1 and go to P2. So this is going to be the vector, and I'm going to call it P1 to P2. Okay, so that's the name of that vector. Okay, so the vector P1 to P2 so the vector P1 to P2 is to take OP2 and subtract OP1. So OP2 is this vector X2, Y2, Z2, and I'm going to subtract off X1, Y1, Z1. And so that's going to give me the vector X2 minus X1, Y2 minus Y1, and Z2 minus Z1. So that's how you find the vector from any 2 points. Okay. I can also write it like this, the vector from P1, which is X1, X2, X1, Y1, Z1, to P2, which is X2, Y2, and Z2, is the vector P1, P2. And that is X2 minus X1, I, plus Y2 minus Y1, j plus z2 minus z1. Okay. Okay. Questions?
No.
Okay. All right. So now let's talk about the magnitude of a vector. So we talked about magnitude in when we had two-dimensional vectors. So the magnitude or the length of a vector so if you remember when we were in 2 dimensions, so let's recall. Given the vector u equal to u1, u2, the length of u1, u2, of the length of u is the square root of u1 squared plus u2 squared. So what do you do with a 3-dimensional vector? Okay, well, with a 3-dimensional vector, we're going to think of it as such. We're going to draw this. So I'm going to start off with this here. And I'm going to drop this and make this perpendicular. There we go. And then draw a line like that. Okay. All right, so now there's the 90-degree angle. So I'm going to let A be here. And then this is going to be the vector A1I. And then I'm going to let the this be the vector A2J. Okay. And then I'm going to stand another vector. Excuse me. So this is A1I, A2J. And then I'm going to stand the vector up in the air like this. That is perpendicular to the ground. So that's perpendicular to the ground. Okay. And so this is going to be the vector A3. And so here is the actual vector. And this vector is A1I plus A2J plus A3K. And it's going to this point, which is P. Okay, so by the Pythagorean theorem, I need to make this point B and this point C. Okay, so by the Pythagorean theorem, the length of AC squared is the length of AB squared plus the length of BC squared. So therefore, the length of this one this vector is the vector A1I plus A2J. Okay. So the length of AC squared is A1 squared plus A2 squared. But now the length of AP squared is going to be the length of AC squared plus the length of CP squared. So now I get the length of AP squared is A1 squared plus A2 squared. And the length of CP squared is A3 squared. So that says the length of AP is the square root of A1 squared plus A2 squared plus A3 squared. But AP is just the vector AI. So that means the length of the vector A1I plus A2J plus A3K is just like before, the square of the components. So that's the length. Okay. So therefore, by definition, I'm having trouble writing it down. Really just not. Given a vector, which looks like A1, A2, A3, then the length of A I want that to be a small a. I don't like it to be a big A. Then the length of A the magnitude for the length of A is A2 squared plus A3 squared in the square root. Okay. All right. We can talk about a sphere. Okay. So a sphere is just a graph of all the points that are a distance A from a central point. So the sphere is a graph of all the points P being X, Y, Z that are a distance r from a central point. E naught. So if I started a circle, a point, and I look at all the points in all directions. So I'm not just going in the XY plane, but I'm going in 3 space. Okay, so I need all the points that are a distance r. So that means that the distance or the length of any point P naught P, that squared is going to be, well, what is P naught P? P naught P looks like X minus X naught, Y minus Y naught, and Z minus Z naught. So therefore, the length of that is X minus X naught squared plus Y minus Y naught squared plus Z minus Z naught squared, and then I'm going to take the square root and I said that distance is r. So therefore you get X minus X naught squared plus Y minus Y naught plus Z minus Z naught squared is r squared. So this is what a sphere looks like. That's the equation of a sphere. With center the point P naught being X naught, Y naught, and Z naught. Okay. All righty. So I'm going to stop that.